Okay, 4.5 global wind patterns. Basically, what are the general trends that we see in wind all over the globe? Here in Long Beach, in general, we see winds coming out of the west, coming from the Pacific Ocean over the land towards the mountains. Every once in a while, we have that reverse. The winds come out of the southeast to the east. Those Santa Ana winds, and those you might have experienced them before. They just kind of feel a little bit different, like a little bit different from normal. So let's get into these general trends. Let's see. Hold on. There we go. Again, enduring understandings. There's a state of balance. One thing that we'll be seeing driving all of this is the heating of Earth's surface and the air. And this is uneven. Do a better job at that. Uneven. Okay. And because it's uneven, causes the wind to air to move, and that creates the wind. And just that balancing out of density that you talked about, you've learned about before, and we'll get into that shortly. But let me write that in density. Density. All about density and uneven heating. You just think the Earth's spinning. We know that Earth is at an angle. We know that the surface is not being heated up equally. So environmental factors resulting in atmospheric circulation. Factors like land. We have different surfaces like land versus the ocean, and we have glaciers in some places. We have deserts. We have forests. And we also have the spinning of the Earth. Those are all factors that affect how wind circulates around the Earth. I think I mentioned today in class how it was really interesting. I think 20 years ago I learned that, or 15 years ago, that a lot of the coal pollution, the pollution is created when coal is burned in China and ends up here in California, and we breathe it in. Alright, sorry it's kind of glitchy. I've been having some weird things on my computer happen. So check this out. A lot of things, these patterns resulting from the different intensities of solar radiation. Most of, as we've been talking about, most of the energy from the sun is hitting that equator for most of the year. It has the most direct rays, and that creates density differences in the air, and something that's called the Coriolis Effect. And that's interesting. It has to do with when you try to move somewhere across the Earth's surface, as you're moving, the Earth is moving too. And if you're in the air or in the water, it creates some interesting patterns. But look, checking out this map, I want to draw your attention to the equator right here. When I just look at the map, I just kind of think, okay, the first little, down a little bit in South America, that's the equator. I always tend to think it's like, in my mind, for some reason, it's like right in between North and South America, but it isn't. You gotta go down in South America a little bit, and they basically cut off that top part of Africa. Then you go straight through Lake Victoria, which is a good landmark, and then kind of straight through Indonesia. And if we look at this zone, this is where you're going to get the most intense radiation. But I think I got to sneeze. Hold on. Okay, got rid of that. You're looking for the most intense radiation. You're looking for this purple, and almost this really light purple, and we see it here like in Australia, North Africa, Middle East, South Africa, and then this little chunk of South America, and we got in this American Southwest and this upper part of Mexico. It's not right in the middle, which is where the sun is most intense, but I want you to think, why might that be? What could be blocking the sunlight from hitting? Something is blocking the sunlight. And what's doing that? Because remember, this is kilowatts per hours per meter. We should see the most intensity at the equator. And at the equator, we really see a similar intensity here as we do up here in the Midwest or up here in Europe. So why is that? Well, the answer is clouds. Okay, clouds are blocking that sunlight. Maybe some of you came up with that just right now in your mind. And really where I circled, you guys know these are the main deserts, right? Southwest Desert, Sonoran Desert, the Atacama Desert of Chile, I can't remember, the Namib Desert, the Sahara Desert, and I can't remember what they call Australian Desert over here. But these are our major deserts, and there were areas where there's not much clouds happening, and we'll get into why that is and why there's clouds at the equator. Why are there so many clouds at the equator? Before we do that, though, I just want you to go ahead and take your colors and go ahead and color this map using this map as a guide, highlighting the areas with the most and the least insolation. All right, moving on. Let's check out why we see that. Remember, we're having the most intense sun rays happening at the equator. Let me go ahead. Let me fill out. I can't really. I'm gonna have to use pointers. At the equator, we look at the belt around the world. We tend to see, rainforests or fairly thick forests, and then right above it, in those areas that I was mentioning, you can tell from the graphics, we see deserts. And what happens is when those intense sun rays are striking the equator, this warm, moist air rises. Warm. So you're creating just a tremendous amount of moisture right at the equator, and that warm air is less dense and it rises. Just like a hot air balloon, right? Hot air balloon rises because it's hot. Well, when that air gets up to a certain elevation, it cools down. That creates clouds, and that creates the rain. So the reason why you have that blocking off of the solar insolation or insolation at the equator is because you're creating all those clouds because of the heat. And then you have rainfall, and you can see there's these forests and rainforests here. Well, that air eventually runs out of moisture, cools down, and then descends. And then, it's cool, so it's denser, and it's dry now. And when it does that, it's not creating clouds. It's sinking down, and that's where you find these desert regions. And this kind of little the little cell, they call it a Hadley cell, of that rising moist air condensing, losing its moisture, and then descending again. So that's why you see these deserts in the areas that we saw before. And then right above the cool, dry desert area, you see areas where there's rain again, because of the that air's then going to heat up because it's near the those deserts. That land is getting warm, and that's going to then rise up and take moisture with it, and then cause rain in those mid latitudes. And we'll see that in the forests like of North America, in Europe, and in South America, well, like in Indonesia. Well, actually, and then parts south of the Amazon basin. But let's take a look. This is what we're talking about. This whole area in here. This is that area that's going to be a little less solar insolation because it's going to be really cloudy. And we can look across that whole zone, and we see, by and large, a lot of forests, a lot of green, right? And so that's the cool, the warm, moist air. And then we look right above it, and for the most part, we're getting that cool, dry. And that's going down. Remember, that's where we're seeing more of the of that intense rain, or intense insolation. And then above that, we have areas that tend to be a little more rain prone. Although it looks like, now you'll see it's not a perfect model because there's definitely local climate variations, one of which you see Southeast Asia being, and China being pretty forested, and that's from the interaction of air currents and the Himalayas. So mountains like the Himalayas definitely affect rain patterns. In fact, Africa used to be pretty much all green until the Himalayas formed. Like India used to be way down here, and then all of a sudden, about 50 million years ago, it started to move north really fast and then smash into Asia. And that basically took half the water away from Africa. So as you can see, it's really striking when you look at this. Just see some of these really dry areas, North Africa and the Middle East, just being super dry, as well as most of Australia, and the American West is very dry. All right, now let's check out. These are the major wind patterns that we see. Let's fill this out. Cold air at the poles, of course. Got warm air at the equator. We'll label that here. And you have these different wind patterns. The very top, coming down from the North Pole. Well, I put in too many letters there. We got easterlies. They generally come out of the east. It's a little, for me, it makes sense to talk about which way the direction of the wind is traveling. But when we talk about a lot of wind patterns, it's where it's coming from. That's where it gets its name. Right below it, coming, from say the middle of the North America, or say the United States, going towards the east, these are called, you can guess it, the westerlies. And it's the same thing in the south. It's the same exact trend in the South Pole or Southern Hemisphere as well. And then we have the trade winds. And it's interesting, you know, you think about the Europeans that came to the United States, Columbus, and afterwards, you know, they were coming on these trade winds. That's probably why they were called trade winds. I'm not quite sure about that. So they would use those to come to North America, South America, and then primarily they would use the westerlies to go back to Europe, more or less. And so you can see just the general pattern. If you look at the equator, there's these wind patterns that are kind of moving to the left, and right below it there's wind patterns that are moving to the right. This would be a good diagram for you guys to color and fill out. So back to some basic science here. You know, when you heat something up, anything, it causes the molecules in it to move faster. And that makes sense, right? That's why something heats up. If you have something compressed, it's hitting the inside of the container, causing, you know, a rise in temperature. And it's interesting because, creates lower air pressure. And that's, you know, we see it rise. And would you rather fly in cold temperatures or hotter temperatures? Well, which one of these groups of air do you think would a plane be able to use most effectively? A denser column or mass of air or a less dense? You can imagine the airplane's going to do better the more molecules it can interact with. There's going to be more lift. So airplane performance is poorer in hotter temperatures. So if there's an issue, now this, of course, the planes can fly and they don't usually at least shut down if it's too hot, but it could make a difference in some situations. So densely packed here, and then loosely or diffused air molecules in those warmer temperatures. All right, so I'm going to go ahead and break this up. This will be part 1, and I'll be doing part 2 in a second.